Good morning. It is Monday, February the 13th, 2023. It is now 10 a.m. and no one has joined the Zoom session. I am somewhat concerned and somewhat frustrated. Many students have requested interaction with the instructor in lieu of short of having to physically come to campus, and so this is the option that we have tried to provide. But unfortunately, a number of you are not taking advantage of that. It also seems evident based on the scores on exam 2 that many of you are perhaps not watching the recording that is being provided. And so I just have some concerns. So I hope you will take that to heart and either begin attending the Zoom session if your schedule permits. If your schedule does not permit, then I would strongly encourage you to begin watching the Zoom recordings. So I am going to sit here and talk to myself as if I were teaching the class so that you have the benefit of the instruction. I do not know that I will continue to do it this way because, again, it's kind of weird to sit here and talk to myself. So let me share my screen. So today is Monday, February the 13th, 2023. I don't suppose there's any questions that I can answer for you since no one is in the Zoom room. We are going to continue our discussion of hypothesis testing, which is our primary focus for the remainder of the semester. We're going to look at the one mean t-test today, and we're going to use the examples that were included at the end of the fill-in-the-blank notes that I provided last week. You will also be responsible for completing class participation number 9 related to hypothesis testing. And then I am going to go ahead and work ahead a little bit and begin looking at chi-square goodness of fit because we will not meet in Zoom on Monday, February the 20th, 2023. I have a personal appointment that cannot be missed, and so we will not meet in Zoom on Monday, February the 20th of 2023. We will, however, meet Wednesday, February the 15th in 2 days at 9:30 for our regular Zoom session. So I'm going to move on over to the fill-in-the-blank notes. Again, these were the fill-in-the-blank notes that we worked on last week. We filled in, we walked through the hypothesis testing process. We then focused on one mean z-test and did several examples there. So I'm going to pick up this morning and look at the one mean t-test. I did provide, and I copied them onto this document, and I will post it into the Zoom recording folder. I went ahead and have provided the keystrokes for Minitab for the one mean or one sample t-test. It's very similar to the keystrokes we had for the one mean z or the one sample z. So it's there for you to follow. The primary difference, if you'll recall, and we talked about this last week, between a z and a t-test is whether or not you know the population standard deviation. If you know the population standard deviation, then you must use it and you conduct a Z, as in zebra, test. If you do not know the population standard deviation, then you conduct a one mean t test, T as in tiger. So this morning, that's going to be our focus, and you'll see as we read through these problems that you are not given the population standard deviation. Again, you need the same kind of information that we needed before. You still have to know the population mean, the sample mean, the sample standard deviation, the sample size, and the confidence, or excuse me, the significance level, all of which should be given in the problem. So we're going to begin with, it's actually example number 4 on that particular handout. It's the first one that I am going to look at this morning. So the question reads, a lumber company is making doors that are 2,058 millimeters tall. If the doors are too long, they must be trimmed. And if the doors are too short, they cannot be used. A sample of 24 doors is made, and it is found that the mean height of the doors is 2,045 millimeters with a sample standard deviation of 33. Using a 0.01 significance level, determine if the doors are either too long or too short. Assume the population is normally distributed. Okay, so one of the first questions that you really have to answer, and I believe it is this way on your test for Module 3, it's also that way on your homework, is which test you're going to conduct. Now, at this point, we have discussed the one mean Z, as in zebra test. And then at this particular moment, we are looking at the one mean t-test. So that kind of gives the answer away, but which test to conduct? We are going to do the one mean t-test because I do not know the population standard deviation, which is sigma. If you go back and scan through this problem, nowhere in the problem does it provide or give you the population standard deviation. In fact, what it does give you is the sample standard deviation. So I know that I'm going to do a t-test. The first step in any hypothesis test is to state the hypotheses. And there are 2 of them, if you'll remember. You have H sub O, which is the null hypothesis, and the null hypothesis must always contain equal in some format. And then you have H sub A, which is the alternative. And the alternative does not contain equal in any form. You, as the researcher, reading the question or setting up the question yourself, have to decide which hypothesis you have. Again, when you're looking for the hypothesis, you want to look for words like believe, think, determine, claim, want to know. And so near the end of this problem, it says, using a 0.01 significance level, determine if the doors are either too long or too short. So then I have to think about mathematically, what would it mean for the doors to be too long or too short? We want the doors to be 2,058 millimeters tall. So if they're too long, they're more than that. If they're too short, they're less, meaning they're not the same. They're not equal to the 2058 millimeters that we need. So the idea that it's too long or too short, when you have that choice, mathematically implies not equal, which would be this symbol. Because it is not equal, that means that that particular statement is the alternative hypothesis. So our alternative hypothesis here is that the mean length of the doors does not equal the required 2058 millimeters. And that's the one that's given, and I'm going to indicate that that's the one that's given. The null is the exact opposite of the alternative. And so the opposite of not equal would be that it's equal. So I've stated my hypotheses. The second step in the process is to identify the players. We have to identify all of the information that we need to work the problem. Now, I'm about to tell you what it is, but should you forget, if you'll scroll back up on our fill in the blank notes under step 3, I tell you for a one mean t-test, you have to know the population mean, the sample standard deviation, the sample mean, the sample size, and the level of significance. So under step 3, okay, which is on page 2 of the handout, so I need mu, which is the population mean, which comes from the hypothesis. I need the sample standard deviation, which is given in the problem. I need the sample mean, which is given in the problem. I need the sample size, which is given in the problem. I need the level of significance, which is given in the problem. But in Minitab, remember, Minitab wants us to use the confidence level. So I can figure out the corresponding confidence level based on my significance level. So I'm going to scroll back up here and I'm going to read through this problem and highlight some things. Okay. First of all, my population mean, which comes from the hypothesis, is the 2058 because that's the length that I want the doors to be. Sorry, I got an extra 0 there. Okay, then let's go back and read. It says, a sample of 24 doors is made, and the mean height of the doors is 2045 with a sample standard deviation of 33 using a 0.01 significance level. Okay, so everything is identified. My sample size is 24. The sample mean was 2,045. The sample standard deviation was 33. And they tell us to use a 0.01 level of significance, or a 1%. So if my level of significance is 1%, that means my confidence level is 99%. Remember, they have to total to 100. So I've identified all of the information from the problem that I need. Step 3 is to calculate the test statistic and its p-value. And we do that in Minitab. And again, I have the keystrokes that you need up there at the top of this page. So it was at the top of page 10. Okay, so I'm going to walk us through it. We're going out to Minitab. We go to Stat, Basic Statistics, 1 sample T as in tiger. I am using summarized data. My sample size given in the problem was 24. My sample mean was 2,045. My standard deviation was 33. I am performing a hypothesis test. I wanted the doors to be 2,058 millimeters. Options. My confidence level is 99% because we were asked to use a level of significance of 0.01 or 1%. And my alternative hypothesis does say not equal because they're either too long or too short. I click OK. I click OK. Very similar to the steps we used for the z-test. Then I scroll down to test. I'm going to copy this over to my page. Whoops, wrong one. Okay, so you have your test statistic. The test statistic is my t-value, which is clearly labeled. So my t-test statistic is negative 1.93. The corresponding p-value is 0.066. And again, that is clearly given here, and I'll highlight it in a different way, slightly different color. Okay, I'm reading it directly from the Minitab printout. Okay, then we move to step 4. In step 4, we make a decision by comparing the p-value and the level of significance. We use the same guidelines as we had before. Again, if you don't remember those guidelines, if you scroll back up, I believe they're under step 4. Nope, step 5, I'm sorry. Step 5, which is on page 3. Okay, step 5. If P is less than or equal to the level of significance, then you reject the null. If it's greater, then you fail to reject the null. So I'm going to make that comparison. Let me get back to the page. Okay, so I'm going to compare the p-value, which we get from Minitab, which is 0.066, to the level of significance given in the problem, which is 0.01. I compare them digit for digit. The first digit after the decimal is 0 for both of them. The second digit for the p-value is a 6. For alpha, or the level of significance, is a 1. 6 is greater than 1. So the p-value is greater than alpha. So we fail to reject the null. If we fail to reject the null, that means that the null is true or valid. And we write our conclusion in terms of that true hypothesis. So step 5 is to write a conclusion. In the conclusion, you always include your level of significance. So we would have, at the 0.01 level of significance, the doors are not too long or too short for the required 2058.0 millimeters. Okay, we proved that it was equal to the 2058, meaning they're not too long or too short. All right, moving on. Example number 2 says, an article in the Atlanta Journal stated that students in the University of Georgia system take 4.5 years on average to finish their undergraduate degrees. Suppose you believe that the mean time for undergraduate degree completion is longer. You conduct a survey of 49 students and obtain a sample mean of 5.1 with a sample standard deviation of 1.2. Test your claim at the 0.01 level of significance. So my first thing is to decide which test to conduct. Now, again, at this point, I've only talked about 2 different tests, either the one mean Z or the one mean T. I know that I'm going to do a one mean t-test because I do not know the population standard deviation. Now, guys, on the test for Module 3, the problems are going to be mixed together. So you are going to have to decide which test to do based on the information given. Again, we always do a one mean t if we do not know the population standard deviation. And then I'm going to begin my hypothesis testing process. Step 1 in the process is to state the hypotheses. So I have H sub O, which is my null. It's on the top when you are handwriting it. The alternative is on the bottom. Okay, remember the null has to contain equal in some form. The alternative does not have equal. Again, this one may read a little differently from what you're used to seeing, okay, because at the end it says test your claim at the 0.01 level. Well, if you go back to the second sentence, it says, suppose you believe that the mean time for undergraduate degree completion is longer. Well, longer than what? It's longer than the claim in the Atlanta Journal of 4.5 years. You have to kind of put all the pieces together. So your claim is that the mean is longer. If I think about the word longer, mathematically, I'm thinking greater than, which would be this math symbol, which does not include an equal. So that statement, all those pieces put together, is my alternative hypothesis. So I would say that the mean time for undergraduate degree completion is longer than the 4.5 years that it claims in the Atlanta Journal article. And again, that's the one that's given. I know that my null hypothesis is the exact opposite. The opposite of the null is that the mean is less than or equal to 4.5 years. Remember, the null must always contain equal. And the null and the alternative are inverses or opposites of each other. Step 2 in the process is to identify the players. Again, collect, write out, identify all of the information that you need from the problem. You need the population mean, the sample standard deviation, the sample mean, the sample size, the level of significance, which also leads us to the confidence level. So again, from my hypothesis, I know that my population mean is 4.5 years. Then I'm going back to scan or read through my problem again. Okay, it says in the Atlanta Journal, 4.5, you conduct a survey of 49 students and obtain a sample mean of 5.1 with a sample standard deviation of 1.2. Test your claim at the 0.01 significance level. Everything you need is given in the problem. So it tells me that I sampled 49 students. We got a sample mean of 5.1. We had a standard deviation, I believe it was 1.2, but I'm going back up to check. Yep, sample standard deviation of 1.2. It says test the claim at the 0.01. So my significance level is 0.01 or 1%, which means my confidence level is 99%. Everything I need to work the problem is given. Step 3 is to calculate the test statistic and its p-value. And we're going to do that in Minitab. So I'm going over to Minitab, starting over. Stat, basic statistics, display descriptive statistics. Whoops, I'm sorry. Wrong command. Sorry, my fault. Stat, basic statistics, one sample T. Again, I have summarized data. My sample size was 49. My sample mean was 5.1. My standard deviation was 1.2. My hypothesized mean was 4.5. It is a 99% confidence level, and we were saying it was longer or greater than. Make sure you change that. That affects the calculation. Okay. Okay. And we get our results. So my T test statistic from Minitab is 3.50. The corresponding p-value is 0.001. Then we go to step 4. Step 4 is we make a decision. By comparing the p-value to the level of significance. Okay, so my p-value, which comes from Minitab, is 0.001. My level of significance, alpha, is given in the problem is 0.01. Again, we're going to make the comparison digit for digit. So the first number after the decimal is 0 in both cases. The second number, I have a 0 for the p-value and a 1 for alpha. 0 is less than 1, so the p-value is less than or equal to alpha. The guidelines back on page 3 tell me if the p-value is less than or equal to alpha, that we reject the null. If we reject the null, that means the null is false or wrong, and the alternative is true or correct. So we've proven, we go back up here and look at our hypotheses, we have proven that the alternative is true, which means it does take longer than 4.5 years to complete the degree. So we would say in our conclusion, which is the 5th step, at the 0.01 level of significance the mean time, and let's see how they had it worded in the problem. It's easy if you kind of take the words from the problem. The mean time to finish, mean time for undergraduate degree completion. So the mean time for undergraduate degree completion is longer than 4.5 years. Okay, I'm going to leave question 6 so that if you want to practice one on your own, you have that available. But I do want to go down to number 7, which I don't think is actually on your current handout. So you can print it off later. Okay, it'll be page 13. And it's a little bit different. And I have the Minitab keystrokes there at the top of page 12. Question 7 says, statistics students believe that the mean score on the first statistics test is 65. A statistics instructor thinks the mean score is 65. He samples 10 statistics students and obtains the scores. He performs a hypothesis test using a 5% level of significance, and the data is assumed to be from a normal distribution. This problem is different from the ones we've been looking at because this particular problem gives us the raw data. It gives us the list of the 10 scores. It does not give us the summarized statistics. It doesn't tell us what the sample mean is. It does not tell us what the sample standard deviation is. It does tell us the sample size because I can count how many I have. So this one's a little bit different, but we can still work the problem in Minitab. Minitab will, if you give it the raw data, it will calculate the mean and the standard deviation for the sample behind the scenes when it does the hypothesis test. Okay, so the keystrokes in Minitab are slightly different, and you have to enter the data. Okay, so we're going to walk through this problem together because you may see some problems like this on your homework and on the test for Module 3. The test for Module 3, by the way, and let me go over here and make a note about that before I forget. Okay, the exam, the Module 3 exam opens Wednesday, February 15th, 2023 at 1 p.m. and will close on Sunday, February 19th, 2023 at 11:30 p.m. So you'll have to take the Module 3 exam in that window. The Module 3 exam will cover confidence intervals for Z, confidence intervals for T, a 1 mean Z hypothesis test, and a 1 mean T hypothesis test. So again, you need to be aware of that the Module 3 exam is coming up fast and furious. Okay, we only have about a week and a half, 2 weeks left in the course. So we are progressing right along. Okay, so let's look at how to work this problem when I have the raw data. We didn't look at any problems for the one mean Z where we had the raw data. We could have, but we don't, because again, typically to do a Z, you have to know the population standard deviation. And if I have that raw data, I likely do not have the population standard deviation. So again, if we begin, we kind of look through this question, we've read it again, and think about which test to conduct. Again, I can still say I'm going to do a one mean t-test because I do not know, am not given the population standard deviation, which is sigma. So even in this question, even though I'm not given like the sample mean, the sample standard deviation, I'm not given the population standard deviation either. So that is my red flag that's waving to say, ooh, I need to do a one mean t-test. We begin the process the same way we begin every hypothesis test. We start by stating the hypotheses. That doesn't change. I have the null hypothesis, which must contain equal in some form, and I have the alternative, which has no equal. Okay, so again, you have to identify the hypothesis looking for the words believe, think, claim. Okay, so this one actually states it twice. It says students believe that the mean score is 65. The instructor thinks the score is 65 and he wants to test that claim. So we think the mean score is 65. The word is in mathematics, in my mind, implies equals. Okay, so this statement would actually be the null. Okay, this statement would actually be the null. So my hypothesis is the mean is 65. That is the null. The mean is 65. That's the one that's given. So my alternative, which is the exact opposite, would be that the mean does not equal 65. Mean does not equal 65. Then the second step, we still have to identify the players and I still need the same information, but everything is not given to me. Okay, so let's think about this for just a minute. We have to have the population mean. We ultimately need the sample standard deviation, the sample mean, the sample size, the significance level, which leads us to the confidence level. Well, again, the population mean comes from the hypothesis. So we believe it is 65. The problem does, if you look, and read. It tells us he samples 10 statistics students. And even if it didn't tell me that, I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 pieces of data. So my sample size is 10. And it also tells me to test the claim using a 5% level of significance. Now, it's stated in this problem as a percentage. Okay, so 5% is 5 divided by 100, which is 0.05, and makes our confidence level 95%. The two pieces that I do not have are the sample standard deviation and the sample mean. We have the raw data. And so app.minitab.com will calculate these values behind the scenes. But I have to enter the raw data into Minitab. So I need to write down those numbers. So I'm getting my paper and my pencil, and I'm going to write down those 10 numbers. So I have 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. I've written down those 10 scores. So then I'm up to step 3. Step 3, we're going to calculate the test statistic and its p-value. Now again, if you need the keystrokes are on page 14 at the very top. The first thing I'm going to need to do is, because I have the raw data, is I have to enter the data into Minitab. These are the module, or the, let's see, exam 1 scores for statistics. And I'm going to enter those scores that I wrote down: 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. I've got all 10. I'm going to scroll back up, make sure I didn't type something funky. Okay, I have them all typed correctly. So I have entered the raw data. So I go to Stat, Basic Statistics, 1 sample T. This time I want to choose 1 or more samples each in a column, because I have the raw data. I want to choose 1 or more samples each in a column. I then have to tell it where is the data. The data is entered in column 1. My hypothesized mean is that the scores, or the average, was 65. Then I go to options. We're doing a 95% confidence level, and our alternative hypothesis contains the symbol not equal. Okay, I'm going to go through that again. Okay, so we go stat, basic statistics, one sample T. I do not have summarized data. Excuse me. What I have is one or more samples each in a column. So I choose that option. Then I choose the column where the data is located. My hypothesized mean is 65. My confidence level is 95. And my alternative hypothesis contains not equal. I click OK. I click OK again. Now I want to show you two things. If you look here under the descriptive statistics, when you get your results, remember I told you that Minitab would calculate the raw data stuff behind the scenes? Well, it's done that. Okay, let me see if I can get here where I can paste it for you. Okay, well, let me just paste it right here. Paste. Okay, if I look at these descriptive statistics, Minitab, again, has calculated behind the scenes, has calculated my sample mean, and the standard deviation. It's given it to me. Okay, I don't necessarily need it, but should you need it, if they ask for it in the problem, Minitab has provided it. My mean for the sample was 67, and the sample standard deviation was 3.2. I also get in that same command my test statistic, which is what we were really looking for, but I wanted to point out that you did get that information. So my T test statistic is 1.98, and my corresponding p-value is 0.079. Then I move on to step 4. Step 4 is where we make a decision. By comparing the p-value to the level of significance. So I have from Minitab, my p-value is 0.079. My level of significance given in the problem is 0.05 or 5%. I'm then going to compare these numbers digit for digit. 0 is the first number after the decimal. Then I have 7 compared to 5. 7 is greater than 5, so P is greater than alpha, so we fail to reject the null. If we fail to reject the null, that means the null is true. Okay, so the null is true or correct. So in this case, that means it is, or the mean is 65. So last step, step 5, is to write the conclusion. The conclusion should always include the level of significance. So at the 0.05 significance level, the mean score on the first statistics exam is 65. And there you go. Okay, I would ask if there were questions. However, there is no one in the Zoom room. So I don't guess there's any questions. I do want to point out at this point, you can complete class participation 9. We have completed all of the content in module 3. So you can begin preparing for the module 3 exam. But I want to take a look at class participation 9 because the way it is structured is a little bit different from the others. Okay. It says in bold print at the very top of the page, you should only complete 2 questions. 1 question from part 1 and 1 question from part 2. You are using the data from the class survey to determine the sample mean, rounding it to 2 decimal places, and or the sample standard deviation, and you round it to 2 decimal places. You're going to work through a hypothesis test, and I would tell you to do it exactly the way that I've been doing it. Identify the test you're going to do, state the hypotheses, identify the players, calculate your test statistic and p-value, make a decision, and write a conclusion. You have to do all of those things. For part 1, and I tried to color code it where you can see it clearly, if your last name begins with A through M, you will do question 1. If your last name starts with N through Z, for example, Jewel, her last name begins with the letter T, and so she would do question number 2. For part 2, again, it's broken up based on the last letter or the first letter of your last name. So again, for Jewel, whose last name begins with the letter T, she would do question 5. So when she submits class participation number 9, she will have done question number 2 and question number 5 only. Do not do all 5 questions. You only do 2. And which 2 you do is based on the beginning letter of your last name. Okay. As I mentioned earlier, okay, I'll also indicate here you can do the 1 mean T-test homework quiz now as well. It's actually due on Sunday, February the 19th. Class participation 9 will be due on the 19th. Module 3 will open after class on Wednesday. That affords you the opportunity to ask questions should anyone attend the Zoom room. So it is 11 o'clock. I do have an additional hour, and we are going to move ahead, even though we're a little bit ahead of schedule. We're going to begin and shift our focus to the beginning of Module 4. Even in the beginning of Module 4, we are still continuing our conversation of hypothesis testing. We're going to learn some additional hypothesis tests. By the end of the term, you will have learned 5 different hypothesis tests. At this point, you've only learned 2. 1 mean Z and 1 mean T. So I am using a PowerPoint, and I will post it into the Zoom recordings folder because I do not know if this is the one that is in D2L currently or not. So we're going to begin Module 4, and the first topic is chi-square goodness of fit. We're going to actually begin talking about a different type of distribution, okay? A different type of distribution. And that particular distribution is called chi-square. And we'll talk a little bit more about the characteristics of chi-square in a minute. We're going to focus on one of the chi-square uses. Specifically, we're going to focus on chi-square goodness of fit. If you were to take the second half of the statistics course, Stats 2401, which actually starts this semester on March 2nd, it'll be another 8-week course. We talk about all of the different uses of chi-square. Chi-square is actually one of those topics within statistics where you can actually take an entire course, a 15-week course on chi-square. I have done that. I've had an entire course for 15 weeks on chi-square, and we get to look at all of its different uses and how useful it can be. But I want to mention them in case you don't take the second course, but there are really 3 different uses of the chi-square distribution. One is we can use the chi-square distribution to test a claim about a population variance or a population standard deviation. So far, our focus has been on testing a claim about a population mean or the average. But I could also make a claim that the population standard deviation is equal to a specific value or is less than or greater than. And if I'm testing that claim about the population standard deviation or the population variance, then I would use the chi-square test statistic rather than the Z or the T. Secondly, the chi-square distribution can be used to test whether 2 characteristics in a population are associated in some way. Do they affect each other, or are they completely separate values? Do they affect one another? This is called the test of independence, or sometimes the test of association. And again, we do in Stat 1401 talk about this particular use of chi-square. We do not talk about test of independence in this course. But again, I want you to be aware there are multiple uses of the chi-square distribution. The third one is we compare a frequency distribution of observed behavior to what theoretically is expected to happen. In other words, does the distribution fit or follow a specific pattern? This is called goodness of fit, the test for or test of goodness of fit. And this is the one that we are going to focus on. We're going to focus on chi-square goodness of fit. So again, the idea is we're going to look at what we observe and compare it to what is expected theoretically based on the probability that a particular event is going to occur. Again, it's still that connection back to probabilities. So again, we're kind of comparing the observed, what really happened, reality, to kind of the theoretical model, what we would expect, how we would expect something to behave. Some examples of chi-square goodness of fit. Maybe if you're a manufacturer of running shoes, you want to know whether the buyers show a preference for a specific style. Do they like, the high tops better than the lows? Do they like a particular color better than they like another color? Again, that may help you to meet the supply and demand for that particular shoe. A traffic engineer may want to see whether accidents occur more often on some days than on others. Again, thinking about staffing for hospitals, for the fire department, for the ambulance services, knowing whether, if they're going to occur on more days than others. Do they occur at a particular time during that day more so than others? An emergency service. I had a student a couple of years ago who worked for an ambulance service, and he said they would actually do this. They would look at did they get calls at a particular time of day more so than others, again, to make sure that they had enough ambulances available, enough staff on hand, and that sort of thing. So again, we're looking at what reality, what actually occurs, and comparing it to what we think should happen theoretically based on the probabilities. So let's talk a little bit about the chi-square distribution. We've talked about, just as a side note, let me go back over to my note page for just a minute and remind you that so far we have talked about the normal distribution. Okay, so far we've had the normal distribution. Sometimes it's referred to as the Z distribution. But for the normal distribution, we have that nice bell-shaped curve with the mean in the middle that divides it 50-50. And we utilize this normal distribution whenever we are conducting a one mean Z test. The second distribution that we talked about, was the student's T distribution. Let me change colors here. Okay, so we have had the student's T distribution, and it has basically a lot of the same characteristics as the normal, except that it does not taper off as fast. So I still have kind of that bell-shaped curve with the mean in the middle. It is symmetric, but it doesn't taper off as fast, so that you have more area in the tails. And we use it for the one mean t-test. So I'm about to introduce you to a third distribution. The third distribution that we're going to discuss is the chi-square distribution. Okay. So the chi-square distribution, first of all, is not symmetric. I just showed you that the Z, or the normal distribution, and the student's T are symmetric. Most of the data is grouped together in the center. The chi-square distribution is not symmetric. In fact, it is skewed to the right, meaning that most of the data is on the low end, and it tapers off as you get, there's very few on the high end. Lots of values on the low end, very few on the high end. It is skewed to the right. The mean, if you'll remember, for a skewed right distribution is just to the right of the peak. So if I were trying to estimate where it was on this particular graph, you know, I can see my peak. I can get my mouse in the right place. Okay, I can see the peak, and I'm going to be just slightly to the right of the peak. So I would probably estimate my mean being somewhere on this particular graph, maybe about 3, maybe 3.2, 3.3, something like that. Again, it's just an estimation, but it's slightly to the right of the peak. Because the distribution is not symmetric, okay, the values for chi-square will never be negative. If you'll remember, for the z and the t, we could have a negative value, which implies that I'm below the mean. But because the chi-square is not symmetric, okay, those values can never be negative. The lowest it can be is 0, or it will be a positive value. We talked about how that for the normal distribution and the student's t-distribution, we have a different shape of the curve depending upon the number, depending upon the mean and the standard deviation for the z. For the chi-square, it's based on what we call the number of degrees of freedom. For every different degree of freedom, I have a different distribution. It's still going to be right skewed. My values are still going to be 0 or positive, but the shape could be different. Now, I'm not sure that we've talked about, I can't remember if we've talked about degrees of freedom before, but degrees of freedom are the number of values that are free to vary after a sample statistic has been computed. And I want to see if I can kind of give you an explanation of that so you'll kind of have a better understanding of degrees of freedom. So I'm going back over to my notes page, and I want to talk to you a minute about degrees of freedom. You'll usually see it abbreviated DF, degrees of freedom. And again, the explanation for degrees of freedom that you can see here on the PowerPoint slide, and I'll copy it over to our notes page, is that it's the number of values that are free to vary after a sample statistic has been computed. So I want to try to explain this to you via an example. Okay, so let's say that you want to have an average of, let's say, 87 on your quizzes at the end of the term. So we know we want to have an 87. And you have taken quiz 1, quiz 2, quiz 3, and quiz 4. Okay, let's say on quiz 1 you made 93. Quiz 2 you made 82. Quiz 3 you made, let's say, 89. And quiz 4 you made a 77. And you're getting ready to take quiz 5. And we want to know, what do you have to make on quiz 5 in order to get to that 87 that you want to have? Well, we know, or hopefully you know, that we can average things together by adding them up. But the thing is, I don't know what this last value is. So if I add together 93 plus 82 plus 89 plus 77 plus x and divide it by 5, we want that total to be 87. That's how we average things. You total them up and divide by how many you have. Well, let's see if I can add those numbers together using my calculator. 93 plus 82 plus 89 plus 77. I get 341 plus the value that I don't know yet, all divided by 5, and that has to equal 87. Well, that looks like just a good old basic algebra problem. So I'm going to, let's see, multiply both sides by 5 to get rid of the division. So I would have 341 plus x equals 87 times 5 is 435. Remember that on the left, the 5s will divide out. Then I'm going to subtract 341 from either side. So x equals 435 minus 341, which is 94. So you would have to score 94 on that last quiz in order to have an average of 87. And I worked through that to show you that what you have here is you have 1 degree of freedom. Once the first 4 have been predetermined, we can choose what the last one has to be. It is the only one that I can choose or manipulate so that I have the particular average that I wanted at the end. So I have 1 degree of freedom. I have one value that I can choose after all of the others are predetermined. So that's what we mean by a degree of freedom. And that controls the shape of our chi-square. Specifically for the chi-square goodness of fit that we're focusing on, okay, specifically on the chi-square goodness of fit that we're focusing on, our degrees of freedom correspond to the number of categories minus 1. If my degrees of freedom approach are greater than 90%, then my distribution begins to approximate a normal distribution. And I want to try to see if I can show you this. So let me see if I can go out and find a chi-square distribution. Okay, and we can look at some pictures. Okay, for example, if you look at this graph here, okay, the kind of yellow, pukey looking green color has a degree of freedom of 1. If you look at the teal, you have a degree of freedom of 3. Blue, you have a degree of freedom of 4. And again, notice they're still all right skewed, but my peak kind of gets flatter and it's stretched out more. But again, as those degrees of freedom approach 90, and I don't know if I can find one of those, it becomes the normal distribution. Let's see if we can look at this one. Okay, even here, you have degree of 3, degree of 4, degree of 8. even as you get looking at the degree of 8, it begins to look like it's getting closer to that normal distribution. Okay, so as your degrees of freedom increase, then your curve begins to look more and more like the normal distribution. Let's see. Here's another one where you can see it with different values. So it's taking a minute to load, but you have a degree of 1, 3, or 10. Okay, so the primary thing I need you to remember is that the chi-square is not symmetric, and therefore the values for your test statistic chi-square will never be negative. They'll be 0 or positive. A couple of other little side notes that we need before we look at an example. And I want to try to get through one example. I believe I have time to do that. It's 11:20, so I do. Okay. One of the reasons that we focus on chi-square goodness of fit is because it is one of the few test statistics or analyses that we can use with qualitative data. Okay, one of the reasons we're focusing on chi-square goodness of fit is because it can be used with qualitative data. And I do not want you to complete this course thinking that you can never analyze qualitative data, which is words and categories. You can, but again, our options are limited. Another important characteristic, and honestly, Minitab will take care of this for you, is that the number of observed values has to equal the number of expected. Okay, remember, observed is the reality. So if you're looking at this, observed would be your reality, what you actually see happen, and the expected is your theory. Kind of think virtual. Okay. And there are two types of problems that you can encounter with chi-square goodness of fit. And we can talk about having equal proportions where all the categories are the same, or we can have specific proportions for each category. And today I want to look at the equal proportions, and then on Wednesday we'll begin the discussion of specific proportions. One of the changes, the process for hypothesis testing is not going to change. You still are going to state your hypotheses, identify the players or the needed information, calculate your test statistic and its p-value, make a decision, and write a conclusion. So those 5 steps are not changing. A couple of the pieces that do change is how we state our hypotheses. Okay, because now we're going to be looking at qualitative data, which is words or categories, and we're also going to be focusing on the proportion or the percentage as opposed to the mean. And so the way we state that differs, and again, it could differ from researcher to researcher. Some people will write it out in words. Some people will write it out in symbols. It just kind of depends on the researcher. And I will probably likely show you an example of both. So the null hypothesis will say the observed values are match. We could also say that they fit a particular distribution, or they follow a particular distribution. Primarily with chi-squared, you're going to have the null hypothesis will always imply equal, and the alternative will imply not equal. Okay, you don't have to worry about less than, greater than, or equal to, or so forth. The null hypothesis will indicate that they match, are equal, they fit, or they follow the expected distribution. The alternative would say they do not match, they're not equal, they're different. We would say they do not fit or do not follow a particular distribution. So again, you have to be careful of the words, but you have less options because the null will indicate that they're equal. The alternative will indicate that they're not equal. Minitab is going to calculate the expected value for you, but in case you didn't have access to Minitab or to some kind of technology, you could calculate the expected value yourself. You would take the total number of observed values from the sample. How many do you have in the sample? And multiply it times the probability of success. Now, we do probably need to talk about this calculating the probability of success because you may have to do that in order to enter stuff into Minitab. The probability of success is what's the probability that you get the category that you want. And there's only going to be one way to do that. So it's 1 in the numerator divided by the total number of categories that you have. Okay, so the probability of success, remember success means you get what you want. There's going to be one way to do it out of all of the different options. Now again, Minitab is going to calculate the expected value for you. Prior to the advent of the technology where you had the calculator, the computer to help you, you would have to do it by hand. So let's take a look at an example. Okay. It says you are providing sodas for your after-school program. You believe that the flavor of soda does not matter to your students. You poll 100 of your students about 5 different flavors and get the following results. At the 5% level of significance, is your claim true that the students don't care what flavor they get? Okay, so give me just a minute. And I'm going to put in a couple of blank slides so that I can write on them. Okay, so again, if you have to recognize that this is a chi-square goodness of fit, a couple of things help me to do that. Okay, one of the things that helps me in this problem is that there is no mention of the mean. Okay. My data, it talks about we're interested in the flavor of soda. And from the table, I can see that that's a word, which means I have qualitative data. And the only test that we're going to talk about where you use qualitative data in this course is chi-square goodness of fit, and that's the abbreviation. The symbol for chi, which is the Greek letter, let me write it down here, chi-square, the Greek letter chi looks like a big fancy X, and we put an exponent of 2 to show that it's squared, and then goodness of fit, GOF. Okay, so there's no mention of the mean, but it does talk about flavors, which are words. So I have qualitative data. So that's my clue that I'm going to do chi-square goodness of fit. So then the first step in any hypothesis test, as we've been talking about all morning, is to state the hypotheses. You're still going to have a null hypothesis and an alternative hypothesis. The null will contain equal. The alternative for chi-square will contain not equal every time, all the time. We still look for those key words: claim, believe, think, want to know. And so if I look at this last sentence, it says, is your claim true that students, get a different color, sorry. That students don't care which flavor they get. Okay, that's your belief. It says it back up here at the beginning. You believe that the flavor of soda does not matter to your students. Okay, so we're saying flavor does not matter, meaning another way to say that is there is no preference, or flavor does not matter. So all the categories does not matter implies that all categories are the same, that they like, it doesn't matter. Okay, or you can say there is no preference. Okay, so this idea that the flavor doesn't matter implies that all the categories are the same. They like them all the same, or that there's no preference. So mathematically, that implies equal or the same. So that statement that I've got kind of underlined in orange is my hypothesis, and specifically, it is the null hypothesis. Now, again, you can write it in a variety of ways. We could say all flavors of soda are equally liked, that they like them all the same. You could say there is no preference in flavors. I guess you could write they don't care which flavor they get. Okay, they don't care which flavor they get. Again, that implies that they're equal. So the alternative would be all flavors of soda are not equally liked. I add one word and it implies that they're not the same. And again, there's other ways to say that. Okay, you have to kind of use some logic, some reasoning, and think about what's other ways to word it. Okay, but we're trying to say that all the flavors are the same, or all the categories are the same. I'm going to indicate that the null is the one that's given here. So we state our hypothesis. Step 2 is we identify Step 2 in the hypothesis test is we identify the players. Okay. I didn't tell you what you needed earlier for this, but for chi-square goodness of fit, you need your categories. You need the observed, which are given. And you need the expected proportion or percentage for each category. Okay, so the players that you need are the categories and the observed values. Okay, those two things, the categories and the observed, okay, are given in the table. That is given in the table in the scenario. Okay, so in this problem, let me see if I can get back up here to it and I'll copy it. Okay, copy, go down to the next slide. See if it'll let me paste. Okay, so this table that was part of the question gives me my categories. Whoops, sorry. Gives me the categories and it gives me the observed. When I asked 100 students which flavor of soda they preferred, and I wrote it down, I found that 32 of them wanted cherry, 28 strawberry, 16 orange, 14 lime, and 10 grape. Okay, those were my observed. It does not automatically give me the proportion. Okay, but we're trying to say that they are equally likely. So my expected proportion is the same for each category. And I showed you the formula just a minute ago. To find that probability of success, okay, P, which equals probability of success is 1 over the number of categories. Okay, so if I'm trying to say they're equally likely, the category, the probability of success is the same for every category. Probability that I'm going to get cherry is the same as I'm going to get strawberry and so forth. Okay, so I would have probability is 1. There's one way to get cherry out of 5 categories. Probability of strawberry. There's one way to get strawberry out of the 5 options. Orange. There's one way to get orange out of the 5 categories. So it's 1/5, or if you convert that to a decimal, it's 0.2. Okay, so my probability of success is 1/5, 0.2, or 20%. There's a 20% chance that the student would select cherry. there's a 20% chance they would select strawberry, a 20% chance they would select orange, a 20% chance they're going to select lime, a 20% chance they're going to select grape. Okay, so we've identified the players. Then the next step, and I want to try to get through this one problem. Okay, the next step is to calculate the test statistic, which will be our chi-square goodness of fit and its p-value. And again, we're going to use Minitab to do that. And the first thing we have to do is we have to enter this table into Minitab. We have to enter the data. Okay, so we will enter the categories. We're going to put the categories in column 1, and you're going to enter the observed in column 2. Okay, so let me kind of scribble these down. We got cherry, strawberry, orange, lime, and grape. Okay, so I'm going out to Minitab. And I'm going to get me a new worksheet so we don't get confused. Okay, so in column 1, we're going to put the flavors of soda. We had cherry, strawberry, orange, lime, and grape. Okay, then we have our observed, and I'm going to call it observed. 32 students selected cherry, 28 strawberry, 16 orange, 14 lime, and 10 grape. Okay, and then I'll write the keystrokes down, and then I'll put them on the slide for you. Okay, so we go to Stat, Tables, near the bottom, chi-square goodness of fit, test, one variable. Okay, so let me go back over to the slide and write those down for you. Okay, so you enter the data, then we're going to go to Stat, Tables, chi-square goodness of fit test, one variable. Okay, so let's do that. I've entered the data, Stat, Tables, chi-square goodness of fit. I have to tell it where the observed counts are located. They're in column 2. My category names are in column 1. We are doing equal proportions. Equal proportions. Okay, so you go observed counts, where they're located. Let me make you some notes. Okay, so after you get in here, you're going to do indicate where observed values are. Okay, for us, that's C1. Then you're going to select category names. That's C2 for us because of the way we entered our data. Okay. We test the input column for equal proportions. So then we test input column and we have equal proportions because we're trying to say that the flavors are enjoyed equally. Okay. And then I click OK. And at the top of the screen, I get all of my data. Okay, so then we're going to go OK. All right. Let me insert another slide. Okay, so we get, there's our keystrokes, and we get our data. Now, there's a couple of things I want to show you here. Okay, on the initial table, okay, on the initial table called observed and expected counts, okay, observed and expected counts, Minitab, okay, and you can't see it. Let's see. Minitab shows you the observed, okay? So you have the observed. These were the ones that were given. And then you also have the expected. If everything works the way that we think, if they're equally likely, we should have had about 20 students. Okay, so this is your expected. This is your theory. So it does give you those values if you needed them. Minitab calculates what we should expect in theory. Also, under the header chi-square test, we get our test statistic and our p-value. Okay, so from Minitab, we get our test statistic, which is what we were trying to find. Here's our test statistic. So my chi-square goodness of fit test statistic is 18, and the corresponding p-value is 0.001. Then I'm to step 4, where I'm going to make a decision. Okay. Again, by comparing the p-value to the level of significance. So let me see. Let me go back up here. Our level of significance from the original problem says 5%. Okay, so my p-value from Minitab is 0.001 and alpha is 5%. And I'm going to compare those two values. So 0 to 0, 0 to 5. 0 is less than 5, so P is less than or equal to alpha, which means we're going to reject the null. Remember, if we reject the null, that means the null is false or wrong, and the alternative is true. So in this case, if the alternative is true, that means that the flavors are not liked equally. We proved that this statement is true. So all the flavors of soda are not equally liked. Okay? They're not equally liked. So the last step in the hypothesis test, which is always the last step in a hypothesis test, is to write your conclusion. And again, there's different ways you can word it, but you always include the level of significance. So at the 0.05 level of significance. And again, you could say it different ways. We could say the students do care. Okay, we could say the students do care which flavor of soda they get. You could say that all flavors are not equally liked. Now, the one thing that chi-square goodness of fit does not tell us is it doesn't tell us which of the flavors the students prefer over the others. It just tells us that they don't like the flavors equally, that one of the flavors they like better than the others, but it doesn't tell us which one. We would have to do further statistical analyses to determine which of the flavors are preferred or which one they do want over the others. Okay, so I only have 8 minutes left, and I really don't have time to do another example. But again, I want to remind you of a couple of things. We have finished Module 3. You can now do class participation 9, your 1 mean t-test homework, and the Module 3 exam will open on Wednesday, February 15th, 2023 at 1 o'clock, and will close on Sunday the 19th. And yes, I have worked a little bit ahead looking at chi-square goodness of fit, because we will not meet on Monday, February 20th. We will, however, meet on Wednesday, February the 15th.